Thank you, Carlos, for that nice introduction. Probably most of you, or almost all of you, already know me. I'm kind of frequent face here. So first of all, I want to thank especially CITA and all of you guys for the hospitality. Many times you have seen me and you will see me here. So yeah, as Carlos was mentioning, I'm going to talk today about binary neutron-star mergers. And I'm going to focus on gravitational and electromagnetic radiation. Let me first say that this work is in collaboration with these folks here. Again, some of them you already know. You, of course, know Carlos. You probably know Luis as well. Enrico was actually a CITA National Fellow a couple of years ago, so probably you recognize him as well. And the talk I'm going to present today is mostly based in these publications that we have submitted this year. So I will split the talk in two parts. The first part, well, initially I will try to motivate why it's interesting to look at binary neutron-star mergers. Probably that will be not such pain. And in the first part of the talk, I'm going to focus on the electromagnetic radiation coming from such events. In the second part of the talk, I will try to explain how we can use these same binary neutron-star mergers to look at different theories of gravity, in particular a particular case that we have considered, which is the scalar tensor theory of gravity. So just for starting, why consider neutron stars? Well, neutron stars, due to its composition, are very compact objects where probably the strong gravitational field effects are very important. Also, they represent probably the strongest magnetic fields in nature that we can access so far. They are also important for inner engines of pulsars, and they can power as very important astrophysical events. They had a fundamental role in gamma ray bursts, and in addition to that, they can provide a unique signature of gravitational waves. And in particular, the talk today will make emphasis in the electromagnetic counterpart of those gravitational waves. This is a key element for the new generation or the future generation of gravitational wave astronomy. They will also allow us to understand fundamental properties of this object and put harder constraints in the composition and the equation of state of neutron stars. So I was mentioning that we would like to understand better the electromagnetic counterparts of the binary neutron star mergers. And in particular, people have been thinking in two possible scenarios: the precursor emissions or precursor signals. I'm just mentioning two examples here, slash crash cracking or magnetosphere interactions. But there are post-merger emissions, like the proposed kilonova effects due to tidal tails or material ejected from the neutron star mergers, or sheds or gamma ray bursts. Particular, when you had these post-merger emissions, there should be some material coming out from there. In the kilonova case, for instance, you will see that this material has some nuclear decays. And interestingly enough, this mechanism initially proposed was expected to be observed in optical bands. And it was this year, actually, where people have been realizing that the observation can be in infrared or near infrared. Our work now will focus mostly in the magnetosphere interactions. So precursor emissions, but looking at how the magnetospheres of the stars will interact in the highly dynamical regime. So just a brief comment about magnetospheres for a single neutron star. It has been proposed almost in the late 60s that is due or will be generated due to the pair creation cascade process. A good approximation for understanding this magnetosphere is use the force-free approximation. Basically, if the density of the fluid or the energy of the density of the fluid is small compared with the electromagnetic energy, you can use that approximation pretty well. Another characteristic of the magnetosphere is that you will have a closed field region that will correlate with the star until the point of the light cylinder when the magnetic field lines will start to open. These open field lines will produce a sort of wind, and several numerical studies have been done in this field to verify and to check these assumptions and these phenomenological theories. As I mentioned, we want to understand what happened in the case of the binary neutron star system and how these magnetospheres will behave in that case, in particular during the coalescence of the system. So basically, we have a strongly gravitating and highly dynamical system, and we want to see which is the effect in the plasma surrounding the binary. For doing such, we use a general relativistic resisted MHD code, where basically we need to solve the Einstein-Maxwell hydro equations. We use a particular prescription for dealing with the conductivity of the fluid, which is transit between ideal MHD, which will describe the fields inside the star, to a force-free approximation outside the star. The way to do it is to consider that conductivity depending on the fluid density. Just a few points about the code. We use the typical BSSM formulation. We use finite difference for solving the space-time in a Cartesian regular grid. We use high-resolution shock capture schemes for the fluid. We use adapted mesh refinement. And the interesting thing is that for dealing with this particular code, we need to implement an implicit-explicit Runge-Kruta method for the time integration. I will just flash some of the equations that we use. Well, we use the typical 3+1 decomposition. Of course, that for solving this in a consistent manner, we need to properly write or contemplate the hydro equations with the electromagnetic equations. And the way to do it is just to include both parts in the stress energy tensor. We then solve for the equations of motion of the fluids and the electromagnetic fields using conservation laws. And when one considers this resistive MHD has the possibility of generalize the phenomenological prescription of Ohm's law, which is here written in a particular way. So the way that we impose this density current, especially the spatial part of the density current, is writing this part. I just want to emphasize some of the terms. First, you see here a H function, which is a transition function, which allows you to go from the regime inside the star to the regime outside the star, that limit that I was mentioning before between the ideal MHD approximation and the force-free approximation. And then something else that I would like to emphasize here is this quantity chi. That field takes care of these physical constraints, and it's basically non-zero when there is the necessity of being dissipation to release that violation of the constraint. So what I'm trying to say is that this quantity will be a good indication of dissipation and therefore of current sheets in our simulations. As I was mentioning, with this prescription, you can recover the different limits that I was talking, like the ideal MHD, the force-free, each of them valid in each particular regions.
Well, what are mu I and mu ID?
Here?
Yeah, there's a drift velocity.
That's the drift velocity, exactly. So when...
One of them is E cross B, I assume.
Right, so...
Which is which?
So the drift velocity basically takes place when you are outside the star, so in the force-free limit. Inside the star, H is 0, so this term doesn't appear, and you have QB that came from here. And then you have also surviving for inside the star, the sigma E. This is kind of the co-moving electromagnetic field with the fluid.
So H is like a Kerner function?
Exactly, yeah, it's exactly that.
And how does sigma depend on density, if at all?
Here, sigma is just a constant for us. It's a fixed value. So the way that it depends on the density is through H. So it appears here, rho. So basically what I'm saying is that H, if you have your star, here you will have MHD, here you will have force free outside, and H is a function that goes from 0 to 1. And this dependence in the density appears here in this row.
Yeah, no, that I understand.
Okay.
Some was wondering about this, the connectivity. And connectivity is units.
Sorry?
Connectivity is units. So how are you dimensionalizing connectivity? Just to understand exactly what you're doing here.
Right. So so in this case, you can recover. Yeah, let's go back to the previous slide. So if you look at the current density here, J.
No, I understand. Yeah, okay. And J is this is a covariant formula.
Right.
J is equals sigma E.
Right.
But then in the next equation, sigma is become dimensional because H is dimensional. Sigma
Right.
is dimensional. I'm just asking elementary, just be absolutely clear what you're doing.
Okay. So
Sigma is very big, I gather.
yes, in order 10 to the 5, something like that. Okay.
Why is then H squared in the second term in the square bracket? Wouldn't H be good enough?
Here, actually, I think that probably it's enough in the limits where you go to 0 and 1, but then it will take into account this other part of the denominator.
So basically, you're only cleaning E squared minus B squared outside the star in the force field of G.
Right.
That's the only place you need to do it.
Right,
In
right.
the interior, it never happens.
Well, it never happens, but also in the interior, you go to 0, right? So, but yeah, basically, if you want to recover the ideal MHD case, it never happens, yeah.
You can't curve sheets.
Right, right.
And then E dot B is also being cleaned up, I guess. Outside
Right,
the star.
right. But that is a constraint that also happens for the force-free approximation, right?
Right.
Okay. Any other questions? Okay. Okay. So with that in mind, the different configurations that we study and the setups that we propose. Well, let me first say that because we're doing the numerical relativity simulations, we need to start with some initial data, which is generated by the Lorraine library. We actually look at two equal non-rotating neutron stars that we set in quasi-circular orbits separated by approximately 45 kilometers away. We use a polytropic equation of a state, P equal proportional to rho to the gamma. They are low mass stars, 1.6 solar mass, typical radius of 13, 14 kilometers. And what we did was to look at three different configurations. So we set the two stars. This is the angular momentum of the system, so it's rotating like that. And then we set up the magnetic fields. Magnetic fields are of the order 10 to 11 Gauss. And we set up three configurations. One which is aligned, both magnetic fields aligned with the angular momentum of the system. Another case where we have one aligned and the other anti-aligned with the angular momentum system. And a third configuration, which we call the dominant case, where you had only, or not only, but you had one magnetic field and the other is less, way smaller, like 100 times smaller than the previous one. I was mentioning we look also at the gravitational radiation and the dynamics of the system. The system undergoes approximately 2.5 orbits before merger. One thing that we notice is because those values of the magnetic fields, they have negligible effects in the orbits. So basically, all the three simulations proceed in the same way, and they merge roughly in the same time. The final product is a hypermassive differentially rotating neutron star that will promptly collapse into a black hole. So here you see the orbits of the trajectories of the binary. You see the typical characteristic waveform coming from the system, the typical chirp of the waveform. We had longer simulations than this one, but basically, as we want to compare with the electromagnetic counterparts, the main effects there happen in just few orbits before the merger. So coming to the luminosity counterparts, so the electromagnetic counterparts. As I was mentioning initially, there are different mechanisms that one could use to produce electromagnetic emissions. And I was mentioning for the precursor signals that there may be cracking effects and induce emissions due to resonance excitation of the neutron stars. It has been estimated that those energies batches can be of the order of 10 to the 46, 47 ergs per second prior to the merger. The particular case that we can actually study here is more related to the unipolar inductor, which is basically a mechanism for extracting stellar kinetic energy by interaction of the star magnetospheres with a magnetic field. There have been some works already on that, some theoretical models establishing how these things could happen. Just a preliminary estimation, if we write the luminosity for, let's say that we had a magnetized star and an unmagnetized star, very similar to the dominant case that we were proposing. You can write the luminosity of the system as a function that goes as the relative velocity square, the magnetic field square. This is the radius of the dominant star and the companion star, and A is the separation. If you plug typical numbers like the ones that we are using here, you can rewrite this expression in terms of the magnetic field of the primary star and the separation. And basically using the relation of the velocity with the separation through Kepler's law, you can estimate the luminosity for this particular case to be a factor of 10 to the 41 for a magnetic field of 10 to the 11 Gauss. Here I'm using, for instance, a particular orbital frequency that is similar to the orbital frequency of a particle going into a non-spinning black hole, which is a good approximation for the orbital frequency that will go under the plunge. One thing that I would like to notice here is that the dependence of the luminosity goes like the orbital frequency to the 14/3. That's something that will come later. But as I say, this estimation works pretty well if you have this case, a magnetized primary and an unmagnetized secondary. One of the cases that we have, for instance, is both star magnetized. So in this case, this estimation can be not such clear due to the maybe some shielding effects, like basically when the magnetic fields of both stars are equal. In that case, you can compute an effective radius, and your luminosity, instead of being of a dependence of omega to the 14/3, will have a dependence of omega to the 10/3.
Sorry, this is the luminosity produced by what?
In this case, it will be the luminosity produced by the plasma due to interaction with the magnetic fields. So the idea is that you have in these binaries, you will have the two neutron stars, you will have a plasma surrounding both, and the interaction of the plasma with the magnetic fields produced by each of the stars, by this binary, will account for this budget of energy. Okay. So I wanted to present kind of briefly the results that we have obtained for these three particular cases. Here I'm plotting in colors the density of the stars, and in blue lines are represented the magnetic field of each star. This is a typical snapshot of how the merger proceeds, and you can see there is a lot of twistings in the magnetic field lines. This is another typical snapshot, but you are seeing here in color the current sheet, actually. And what you're going to see here is an animation of this merger happening. Again, in blue, you will see the magnetic field lines, and this orange quantity is this scalar field, this field I was talking before, the key, which accounts for the dissipation that will happen in the system. So as you can see, initially, in all the cases, you will see there will be a shear layer between the two stars. And the reason for that is that when you have the two stars moving, it's taking part of the fluid with them, and they are moving in opposite directions. So you have different velocities. What is different in each case is that the configuration of the magnetic fields will be different. When they are aligned, they will try to repel. When they are anti-aligned, they will have reconnections, as in these cases.
So this orange stuff is your chi field?
Exactly, yeah.
So is that mainly pruning E-perp or E-parallel?
Sorry, say again?
That's mainly pruning E-perp, cutting back on E-perp, going from E-perpendicular to B?
Oh, in this case, it's coming from the condition of.
I understand that you don't want E squared to be bigger than B squared.
Exactly, yeah.
But if you're separately canceling off E dot B, then it sounds like what you're doing is preventing the perpendicular component of E from exceeding B.
Right. Yep. So yes, it's coming from there.
And the so this may not physically be dissipation, right? In the sense that what's happening is that when the transverse electric field wants to become larger than the magnetic field physically, that means that any entrained charges, even if they are a tiny fraction of the total energy density, are trying to move faster than the speed of light, which they can't do, and so their inertia becomes important.
Right. Right.
And certainly, large amplitude wave can dissipate in some way or another. But it's not absolutely clear that this does represent dissipation.
Right.
Other than the effects of inertia.
Right. The other quantity that we can look at and has similar feature as this one is the Joule heating, which is E dot B. Yeah. And that quantity also I didn't want to include another plot, but it's basically showing the same patterns as the key field.
If you average over volume, if you sum over the volume, which is the larger term?
I'm not sure about that. I need to look at that. So that was the anti-aligned case, and let me just say that, as you can see, this pattern follows pretty much a spiral pattern representing or following the trajectories of the binary. Here I want to show you it's still the same case, and this represents the magnetic field lines you see in brown and orange, the magnetic field lines, and then in red and blue are the toroidal components of the magnetic field lines. And you can see, so each of these snapshots are every time that the stars cross the XC plane. So it's roughly half orbits. And you can see how the polarity of the magnetic field, so red is positive, blue is negative, like going out of the plane, going into the plane. You can see how the polarity change for every time that the stars cross that plane. Here on the right is the Poynting flux, projected in a sphere at 80 kilometers from the center of the binary. And you can see that, so red is high emission, blue is almost none. You can see that most of the emission is coming through that shear layer, that mid-plane that is rotating with the stars. It will be more interesting when we can see the other cases. But basically, yeah, most of the radiation is coming from that shear layer. This is the second case that we consider. That is the aligned case, where we had both magnetic fields aligned with the angular momentum. You can see here in this snapshot that, in contrast with the previous case, there are no connections, no reconnections between the magnetic field lines. On the other hand, there is a repulsion between them. You are seeing the same quantities here, again, this key field, and how the current sheet, again, here the current sheet happens to start roughly at the light cinder and spreads out, in this sort of a spiral shape, a spiral pattern. And again, you can see here a typical snapshot of that configuration. Let me show you the topology, and the Poynting flags. So the topology is a result that is pretty neat because it resembles the topology of an aligned rotator. And as you can see, the polarities of the toroidal components remain almost the same. You can see the repulsions between the magnetic field lines. And you can see also that in this case, most of the radiation is also coming from the shear layer, this midplane co-rotating with the binary. Let's see the last case, which maybe is kind of the most astrophysical relevant case because it's what you may expect to find in nature. There is basically one of the stars is magnetized. Even when in our simulations we set a non-vanishing value, is practically zero, the value compared to the other magnetic field. And you can see how the non-magnetized star is perturbing the magnetic field lines of the primary star. Let me just, before playing the movie, say that the current sheet now is happening just due to dissipation effects happening behind the secondary star. You can see that in the movie now. So there is a sort of tail that is happening behind the non-magnetized star, probably due to some reconnections. Then at the end, they start to dissipate a bit more, and they finally merge. For the topology, basically, you can see that it's just orbiting dipole with the perturbation of the non-magnetized star, but basically the topology remains the same. And an interesting feature is now, in this case, the radiation is coming mostly through the orbiting plane, so the equatorial plane of the binary, and you see some kind of lamp moving, co-rotating. This lamp actually follows the magnetized star, so where there is more energy coming. So I was mentioning before the luminosities estimates or preliminary estimates for those cases. And one thing that we could see is that basically for all the cases, or in most of the cases, you can make a good agreement of the luminosity with the orbital frequency of the binary. So the blue line here is the anti-aligned case. This is the aligned case, the green one, and the red one is the dominant case. In particular, the red one that we can recall the unipolar inductor model, you can see that the prediction for the unipolar inductor is in pretty good agreement until a certain point. Interestingly enough, when you reach, I should say that at zero is when the stars get in contact. This dashed line represents the maximum peak of gravitational radiation. But at a certain point, when the stars really get close enough, you can see that the behavior of the three cases is pretty similar, indicating that perhaps the highly dynamical effects of gravity is taking control over there. Just to summarize and recap what I was mentioning before, these snapshots are the aligned case, anti-aligned case, and dominant case. And these are snapshots of the Poynting flags again. And you can see, again, how most of the radiation is coming from this shear layer. In this case, it's a bit more collimated than in the other case. But clearly, in both cases, it's more collimated than in the dominant case, where most of the radiation is coming through the orbital plane. Some comments about observability prospects. If we concentrate in the thermal spectrum, the region close to the binary supposed to be optically thick due to the plasma present there. So we can treat that, or we can assume that black body radiation. If we do that and we assume that most of the Poynting flags absorb at the plasma, is more or less roughly equal to the black body radiation emitted by the plasma, then we can estimate the temperature of the order of 10 to the 7. There is a factor of order unity depending on each case. But that estimate allows us to say that most of or in the three cases, the effective temperature will be similar. And then we have a peak in the hard X-ray. On the other case, if you consider a more extreme case, like a magnetar, where the magnetic field can reach values of 10 to the 15, then you expect your luminosities to be powered up for a couple of orders of magnitude, as well as your temperatures, and then you will see emission in the range of the gamma ray burst. With respect to the non-thermal components, there have been several mechanisms proposed, like a relativistic bubble of material injected into the interstellar medium that can lead to synchrotron radiation. There is also proposals saying that maybe happening a strong cooling in the current sheet, and that could allow for having gamma ray via synchrotron radiation or inverse Compton scattering. And finally, something which is kind of interesting, and that's why this plot is here, is the proposal of having magnetic field variation of polarity, giving or resulting in stripped winds from pulsars. In particular, what I'm plotting here is this is the aligned case where you have the magnetic fields aligned with the angular momentum of the system. And again, this is a polarity plot, so this is the perpendicular component of the magnetic fields with respect to the orbital plane. And red is positive, blue is negative. So the main idea is that you have these regions that are switching polarity of the magnetic field component. And this guy had proved that when you have a situation like that, it's possible to have a strong particle acceleration. So that could produce a very, very strong signal of radiation. So with this, I'm finishing the first part of the talk. And I don't know if you have questions, but if not, I will switch gears now and talk about how to use binary neutron stars for.
Last point.
Yep.
Can your simulations just see that wind?
Not in our simulations. No, usually Sironi and Spikowski actually have simulations, but they do the simulations in kind of a confined tube, and it's easy for them to see that. But we can't see that in our simulations. On the one hand, our domain is quite small for that, and yeah. We can see, yes. So this topology we can see, and it's kind of far away from.
You got this polarization switch.
Yeah, yeah.
Polarization, but you don't see the acceleration.
Right.
And why can't you see that? What's the limitation of your simulation?
We basically don't have we don't have the ability for tracking the plasma as they do. Yeah. So in the particular case, they can study that. Basically, they can study just a fluid moving under certain prescriptions of the magnetic field. Here, the situation is.
And the geometry here is very complicated.
Right.
Have you tried testing your force-free fluid? Interacting a force-free fluid with a conducting surface of a simpler configuration, like a flat surface or a cylindrical surface that's aligned with the magnetic field.
The prescription that we are using is based on Carlos' implementation, and Carlos, I think, has a very nice paper where he described the full implementation of the code and different tests, where he tests the collapse of a neutron star.
But have you tested the interaction with the surface?
Uh,
That's a civic question.
yeah, I don't think we have tested the interaction.
I mean, when you have the interacting magnetospheres, then that gets more complicated.
Right.
The first order question is how I conduct the sphere. I mean, there was this paper by.
No, yeah, I know what you mean. Yes.
By Friedman and what's his name, Drell, I think,
Mm-hmm.
which studied this problem with regard to a satellite moving through the Earth's magnetic field. And
Right.
my impression is that they made some quick estimates, but it's not clear that their calculation is relevant in this case because you did a much less highly conducting medium in that terrestrial
Right.
problem.
Yeah, so the case you are mentioning is basically the same as the satellite of Jupiter and Io, right?
Exactly.
Yeah, yeah.
Still, they should be able to see that.
Well, obviously, there are some qualitative effects that, of course, the analysis. But the
Right.
issue is, how good is one doing? Right?
Yeah,
I mean, things look sensible overall, right? But, should we trust your estimates of dissipation rates to the
Yeah, no, that is an excellent question, actually. What we have done is resolution studies. So we have increased the resolution, and the features remain almost the same. But the issue that you are mentioning with the surface is an issue. So,
well, the basic question is like, does that B squared scaling hold? Under what circumstances does it hold?
right. Yeah. Okay. Yes.
That would be a good test to do because you think you know the answer.
Right. Yeah. That's a good point. Yeah. Okay. Any other question or comment? Okay. So yeah, the other thing we can do with binary neutron stars is start to look at different alternative theories of gravity. So we believe that gravity is the right theory to follow. It has passed several stringent constraints from solar system experiments and binary pulsars. But so far, actually, it has been tested only in the weak regime or the low velocity regime. It remains basically untested in the strong field or highly dynamical situations. So one alternative theory or one natural theory that emerged is the scalar tensor theories. The particular scalar tensor theory we are going to focus is the one that has a non-minimally coupled scalar field, where they allow for or has free parameters that can be constrained by the value of those parameters can be constrained by observations. It resembles f of r theories of gravity, which is equivalent to these theories. And in this case, it can be cosmologically motivated if you think about this scalar field as a candidate for dark energy. Also, it's expected, if you believe in string theory, it's expected for a low energy limit of a string theory framework. And then the evolution of compact binaries looks to be excellent candidate for studying gravity in these string conditions and share some light over these theories. So this is a generic scalar tensor theory action, and this phi here is the scalar field I was mentioning. As you can see, this scalar field doesn't couple with matter, though, so it doesn't have this fifth force that some of theories that have been proposed suffer of. In particular, you can recover, choosing properly this omega function phi, you can recover different theories like Brans-Dicke or a Palatini action. The ones that we are interested in is some theories that have been proposed that has an interesting phenomenon known as spontaneous scalarization. This spontaneous scalarization is actually a non-trivial configuration of the scalar field around a neutron star, an isolated neutron star, that has a vanishing asymptotic value of the non-minimal coupling to the matter. So basically what I'm saying is you develop a solution that is preferable in energy configuration that is not zero for the scalar field that the stars will gain. These theories that we are considering can be actually described by two parameters, a coupling parameter of the scalar field, which is known as beta, and this asymptotic value of the scalar field at infinity. One can show that in these cases, far from the star, you can give a prescription of the scalar field like this, which is an expansion in the value of the scalar field. And this factor that appears in 1 over r dependence allows us to define which is the scalar charge of the neutron star, which is basically a measure of how much scalar field the star is accreting. Just to emphasize the difference or observable difference that we can see between CITA and scalar tensors, there appear already at the level of Newton's law. So this is the basic expression for Newton's law in general relativity at linearized level. In a scalar tensor, you have a similar expression, but now G is as effective G, where the scalar charges of the binary appear there. There are effects also in the gravitational radiation at leading orders. So for instance, in gravity, we already know that we have quadruple radiation coming into 2.5 pm. While in scalar tensor theories, there is already a 1.5 term coming from the scalar emission that appears. This term, even when it's interesting because it will take energy out of the system, will not be observable, actually. But as I mentioned, it will have an effect because it's taking energy out of the system. So these theories allow also for imposed observational constraints. As I was mentioning before, the theory is well determined if you set the value of the scalar field at infinity, and you set this value of beta, which is the coupling constant. So using constraints from binary pulsar radiations and solar system experiment, one can constrain the values that you expect to have for beta, for phi 0. So this is one of the typical plots. Just let me mention that in the case that you are interested in these theories to have a spontaneous scalarization, the value of beta should remain negative. If you don't have a negative value of beta, that minimum of potential outside of phi 0 disappear. So we are going to restrict ourselves to values of negative betas just to have this spontaneous scalarization effect. So we perform some full nonlinear numerical relativity simulations of these binary neutron stars. We took a binary separated by approximately 60 kilometers, typical masses, 1.6, 1.8 solar masses, again, a polytropic equation of states. And again, as I was mentioning, we choose, there is a convention always, you can choose beta, positive or negative. I should put a minus here. We are taking negative values of beta according to the constraint, to the observational constraints, and the same for phi 0. And here what I'm showing is different snapshots of the simulation. In black, you will see the contour of the neutron star. And in color code overposed with that, you are seeing the value of the scalar field. So the sequence goes like this. And initially, you can see that one of the stars has a lot of scalar field accreted already. The other has less. As way as the simulation proceeds, the other star catch up the value of the scalar field. Early before the merger, there is a sort of bar structure that develops between the stars. That bar structure is interesting because somehow will trigger the merger to happen faster. And at the end, you see the remnant of the merger of both stars.
The change in the other star occur immediately as relaxation data, or is that what it is?
Sorry, again, the
increase in
the scalar field? No, this is after relaxation. So it happens after. Yeah. So this is a summary of the previous simulation where I'm showing here is the separation of function of time. Just to give you an idea, beta equals 0 is the GR case, so it's when you are recovering actually GR from the scalar tension theory. And beta minus 4.5 is the largest value allowed by observational constraints. So this is the separation as a function of time of the same binary. So you can see how different values of beta are changing according to the different separations are changing according to the different value of beta. The same situation happens when you plot or you look at the gravitational waveforms. You can see how the gravitational waveform is way different from one case to each other. So what is happening in the case of, and this is for, again, the largest value of beta that we can suggest according to the observation, is that the plunge happens almost at 52 kilometers, which is a frequency of about 500 hertz, which is within the advanced LIGO or BIGO band. This effect, it cannot be reproduced even in GR with an exotic equation of state, because in GR the radius of the neutron star is constrained to 14 kilometers. So even if you use an exotic equation of state, not a polytropic one, you cannot have this kind of plunge. I was mentioning before that the particular theory that we observe, we present this feature of spontaneous scalarization, but we have detected also that there is an induced scalarization phenomena that is produced due to the presence of the other stars. So basically, when you have two stars and one has a non-vanishing value of the scalar field, is changing the value of the scalar field that the other star is seeing, is feeling at asymptotically. So that's the phenomenon of induced scalarization. So basically, we can identify three different regimes for the stars when they are far away, and one of the scalar charges is greater than the other one. The dipolar radiation that I was mentioning before that goes like alpha 1 minus alpha 2 is having an important effect. In the intermediate range, when the differences are not so large in the scalar charges, is the dipolar radiation is low, but the effective value of G is changing there. And when they are close enough, and the scalar charge is supposed to be similar, there is no dipolar radiation at all, but the effective G is very different. In addition to that, you have the spontaneous scalarization in binaries, that now it depends on the separation of the binary. So these combined effects allow us to unravel a particular or a combination of both that we denominate dynamical binary scalarization. For following up these studies, what we introduced also was PostNewtonian Formalism, where we basically solved the PostNewtonian equation of motion up to 2.5 order. We combined that with a prescription for evolving the scalar fields. So basically, we propose that based on the expression of the expansion of the scalar field that is felt by the other star, we propose to an algorithm that allows us to account for the effect of the second star in the other star. So it basically goes that you set the value of the scalar field that the star is feeling, either to, if it is the initial iteration, to the asymptotic value of the scalar field, or a better guess, if you are solving for a second time or another step. For each star, you solve the generalized TOB equations, and you guess you have a new guess for the coefficient for the scalar charge, if you want. You update the background of the scalar field, and you repeat these steps until you find a solution. You find a solution basically by different criteria. The criteria you can have is a tolerance in the difference that you are reaching, or something like that. And then you update your scalar charges according to the background scalar field that you are feeling. So with this prescription, it allows us to push the simulations farther away. And what we did also was to validate this prescription with our non-linear simulations. So here in this plot, for instance, you are looking at an equal mass binary case where you have in black dots, the numerical solution from the nonlinear simulation, and then in red and green dots is the solutions including both the induced and spontaneous scalarization effects, and you can see that it reproduces pretty well. This is if you, for instance, if you include just induced scalarization and not spontaneous scalarization there. This is another validation test that we did with, I think this is high mass or different mass ratios. 2 stars, I think is 1.4 and 1.7 solar masses. Again, the dots are the numerical solutions, and the lines here are the PostNewtonian solutions. And you can see the agreement is quite well until the point where probably the PostNewtonian is just not valid because they are too close. These are PostNewtonian evolutions, actually, for equal mass case of 1.5 solar masses and unequal mass case, and how the scalar charges change with the separation of the binary. The other thing that we produce is a set of templates or PostNewtonian waveforms. So by doing these simulations, we can obtain the waveforms of the system, and we're in the process of generating a long template for analyzing with collaborators that can lead to some interesting insights if actually these variations or in the waveforms can be seen or not in the LIGO, in advanced LIGO. So the conclusions for this last part is we observe large deviation from GR that appear not to be captured by weak field analysis. As I mentioned before, these effects we believe cannot be reproduced in GR, even using a different equation of state. There are distinct features that may be detectable with advanced LIGO, even in the late in spiral, Planche, or merge. These features may have even astrophysical implications if you combine the first part of the talk where we analyze the electromagnetic radiation coming from the system, and now you put together this piece of information where the merger is happening in a faster rate, then your electromagnetic radiation can have also a signature of that event. we have proposed a framework to study generic neutron-star binaries in this scalar tensor theory of gravity. And as I mentioned, we are in the process of generating template bank of waveforms for these cases. And that's it.
Any questions? Can you explain the differences between neutron-star, neutron-star, neutron-star black hole?
For the scalar tensor? For the scalar tensor theory, you mean? Yeah, well, it's an interesting question, and it's something that we are planning to look at. But one of the main differences is that in addition to these effects of spontaneous scalarization, there also appears an effect that goes with the gradient of the scalar field. So that term doesn't appear in the neutron-star case. So our prescription or our analysis should include the postNewtonian. Right. There is no Hertz theorem, but there is still present a term that accounts for the gradient, how the scalar field is changing due to the presence of the black hole. So yeah, so we can't do right now still that case, but it will be interesting to see.
So is this something that basically the more cooked up so that it would do something interesting for the scalar field?
So sorry, say again.
Is this the theory that?
Oh, the motivation. Well, no, I think it's a quite interesting motivation, actually. If you come back to the beginning of my talk, and you assume, actually, that, okay, we believe in shear. We know, or we think shear is right. But still, it hasn't been passed the strong regime test, right? I mean, we believe in our simulations. We believe in binary black hole simulations.
No, well, scalar tensor theories are hardly new, and certainly there are specific, implementations of string theory.
Right.
But was he choosing some particular form for potential, or?
Oh, wait. Yeah. Okay. I think I know where you're going. If you recall the expression I used for the action, there is a potential there. In our case, the potential is 0, so there is no potential. So this theory is, I don't know if I mentioned it clearly, but this theory doesn't suffer of these shielding mechanisms, if you want.
This W phi is minus 3,000 minus kappa over 4 beta log.
Yeah, that's right. Yeah.
Okay, where does that come from?
Why that funny form?
I think it's just a form proposed. I don't know if there is a phenomenological explanation. I really don't know. It was proposed by these guys. And the interesting feature is that this expression allows for having this spontaneous localization. And the reason is because when you write the energy of the system, you see, basically you can take the limit. You have a sort of parabola contribution to the energy. Right, and then you add a sort of Gaussian plunge there. And that is what is generating the spontaneous scalarization. I'm not sure I think the motivation may come from ferromagnetism or something like that. I'm really not sure about that. Yeah.
I think I saw once, a year ago, so it's not sharp in my memory, but there's, from some perspective of writing these equations out, this prescription isn't quite as ad hoc and weird as it looks. It's almost like alpha is the first natural charge, and then this beta parameter and the way it comes in is sort of the next natural parameter to come in and kind of a power series expansion of phi. And so there is a way of writing this that it doesn't look quite so contrived, but